So what's really cool about doing space nutrition research is that we get to discover things that we might otherwise not be obvious on Earth, or that it might take years for it to develop.
In March of 2025, your team flew Oyster mushrooms on SpaceX's Fram2 mission, the first human spaceflight over Earth's polar regions, and critically, the first attempt to cultivate mushrooms as a crop in space.
The next step is really, we want to develop a autonomous mushroom growing chamber where you control the humidity, etc. So I would say the most surprising finding is...
Welcome to the Omar Al-Aili podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Al-Aili, and today I'm thrilled to be joined by Dr. Flavia Fayet-Moore, a nutrition scientist, space nutritionist, and the CEO and founder of Food IQ Global. Flavia is the principal investigator behind Mission MushVroom, the first experiment to cultivate mushrooms as a crop in space. And her research spans everything from population-level nutritional adequacy to a paradigm-shifting concept she calls Aeronutrient therapy. Flavia, it's a pleasure to have you here.
Thanks so much for having me, Omar.
Flavia, how do you define optimal nutrition? Not in the textbook sense, but operationally, how does it actually mean for a human body to be nutritionally well supported?
That's such a good question, Omar. And I think it's important we go back to the science of nutrition and how it was actually discovered. Mm-hmm. So when you think back, it's in the late 1800s. We didn't know why, the sailors were getting scurvy. Nobody knew the cure. Same with beriberi, another disease of vitamin deficiency. No, it caused paralysis, and there's researchers all over the world trying to figure out what is the cause. Are they germs? Is it something in the environment? What's happening? And basically, it's, curing scurvy happened when fresh limes, lemons, and juice were given to half the sailors and the other half not. So that was the first clinical trial ever done in nutrition, per se, through food, right, as treatment of a potential disease. And it worked. So then it was like, well, what is in the juice of citrus fruits and in the fruit that cured scurvy, which opened up the whole field of nutrition science. At the same time, you had these researchers looking at what is the cause of beriberi, looking at chicken models of the disease. And this was happening in the Dutch East Indies. Christian Eijkman was one of the scientists. And basically what they found is that once they changed the type of rice that they were feeding these chickens from the refined white rice, which was premium and expensive, and the researcher got banned from giving this premium rice, so he had to pay for the own rice for his own research chickens. And when he started giving the cheap, unrefined brown rice, the chickens miraculously were cured. Right? So again, it led down to the discovery of what is in this component in the bran and the rice that is so powerful that it literally cured paralysis. So that's what led to the discovery of vital amines, because in this case, beriberi is a deficiency of thiamine, which is an amine. And it was vital for life. So the term vital amine was coined. And that's how it was vitamin B for beriberi. And vitamin B was the very first vitamin ever discovered. And that's in the early 1900s. So when you think back, wow, nutrition science is so young. When we look at medicine, it's thousands of years old. Nutrition, it's 120 years ago. We were just discovering that there's this component in food that can lead to very significant health effects that causes death. And the reason why I give that bit of history of like where we're coming from is because it shapes a lot of our mentality around what is optimal nutrition. So all the dietary guidelines in the world today are basically set these requirements from vitamins and minerals to prevent frank deficiency, to prevent scurvy, to prevent beriberi, with a bit of a margin, higher than that to have a buffer, because you want to cover 97% of the population with this recommendation. Now, we know that since the 1900s, nutrition science has moved on. We know that it's not just about energy and the macros, so your carbohydrate, fat, and protein. We know that there's also the micronutrients that are super important, and the micronutrients in doses that aren't just about preventing deficiency, but it's about optimizing the body so it can function from a high performance perspective. So it's like having, let's just put enough fuel for the car to go from A to B, or let's actually put good oil, make sure the water is filtered and it's premium, make sure the fuel quality is clean, so the car is going to be running at an optimal level, not just getting from A to B. So it's the same in the human body. So nutrition, now we know that it's foundational. Everything interacts. That's why we often prioritize whole foods over supplements, because we know that in the whole food, there's thousands of bioactives, it's kind of the newest science where nutrition has gone. It's like, yes, we have vitamins and minerals that prevent deficiency. We now know that at higher levels for some, but not all, because some can be toxic. Optimizes health. And then we know that there's the bioactives that also we don't have a deficiency for, but they're powerful anti-inflammatory, antioxidant, anti-carcinogenic, anti-diabetic, and the list goes on to help maximize health. And they all work together. So it's more than the sum of its parts. The whole food, the whole context, it's all one complex system that interacts with each other. But today, we still look, in our dietary guidelines and the recommended daily intake or daily allowance, depending which country you're in, it's really still comes from that historical prevent deficiency perspective rather than let's optimize health. And that's really where we're moving towards in nutrition, is that we've got to think of the whole complex systems thinking, which that's why I love space. Because space forces you to think complex systems thinking. You can't just look at just protein or just fat or just the micronutrients. It's how they all interact together, because they're in one big, complex, beautiful system that are all dependent on each other. So if you're talking about what is optimal nutrition, is when you have enough of the vitamins, the minerals, the protein, the fat, to help, the neurotransmitters to be made, to be converted into the active form, be for it to communicate with the other cells, to get glucose into the cells in the brain to function. It works at every single cellular level in the body. And that's why I love nutrition, because there is not one system that is not affected by nutrition. And only now we're starting to realize, at least from a medical perspective, how significant that effect is. So optimal nutrition is when you're not just meeting the requirements for basic function and to prevent deficiency, but in a system where you're fueling your car for performance and ensuring that all the different components are there and that all the maintenance that's needed to keep everything functioning is there as well.
Great. Flavia, your research distinguishes between nutrient adequacy and nutrient priority. What's the difference, and why does that distinction matter for how we think about dietary guidelines, which you just mentioned?
Yeah, so this research that you're talking about is called the priority nutrients. We've published 2 papers on it, one in Australia and New Zealand and one looking at the US. And what we did is we looked at a population to go, well, what is the level of micronutrient and nutrients, so your macros or micros? What is the level of nutrient deficiency in the country? And then we profiled all the different nutrients and what level, people are consuming them at, or what level their nutritional status is at, blood markers and biomarkers. And then we looked at all the science on should these requirements, based on the reference values that were set in 2006, which means that it's based on science from like 2003, more than 20 years old. Let's do an update and see which nutrients do we maybe require a bit more based on the latest nutrition science. And then we took that and went, okay, what are the nutrients that have the greatest association with disease prevention? So things like cardiovascular disease, type 2 diabetes. And then we said, well, of all these diseases, what are the priority ones for each country? What are the things killing the most people, right? So Alzheimer's is up there now. Cardiovascular disease is shortly thereafter. They're the priority nutrients. To then go, well, where is the government policy intervention going to get the biggest bang for their buck across the population, from young children all the way to the elderly? And that's how we profiled with the science and looking at the totality of the evidence to go, what are these priority nutrients that are going to help? So there were, in Australia and New Zealand, there were 6 priority nutrients: vitamin D, calcium, magnesium, folate, omega-3, and fiber. So they're the nutrients that are key to help population not only improve their health, but ensure that we're correcting deficiency. Now, what was most shocking from this research is that 22 out of the 31 nutrients we looked at, that there were data, or shortfall nutrients in at least one demographic group in the population.
Yep.
22 out of, like, it's insane. So when you think of what I just said before, that nutrition affects every single system in the body, and that it's not just, the body starts compromising when it's suboptimal. It's not just to get the deficiency, like a disease. It already starts failing when there isn't enough water in the car, right? When there's impurities in the fuel and the filter is clogged up. So it's not going to function. It might not die, but it will start failing. So it just shows the level of concern that we have. And the same thing was in the US. There's another study published by Harvard showing that there's more than 15 micronutrient shortfalls across the globe, over 180 countries. It's a huge problem. So even though nutrition science has moved on and we're now kind of looking at the bioactive, the food synergy, and the whole food complexity, we're still not even meeting our nutrient requirements for basic needs. And the real reason around that is that a third of our calories are coming from food that is not nutrient dense. Okay. So it's a very complex issue, right? Because it's a food system issue, it's behavioral, it's education. You can't like blame one thing, but it's actually a big problem because the populations around the world are not getting enough nutrition to function optimally. And we are having high rates already of also deficiencies in populations because of these shortfalls.
Okay, great. So walk me through the cascade. When a population is chronically suboptimal in a nutrition like vitamin D or magnesium, not clinically deficient, but just consistently below recommended intake, what's happening physiologically over months and years to the human body?
Yeah, so when you think about all the vitamins and minerals, most of them take, let's say you were to stop getting enough vitamin D, or you were to stop getting enough thiamine, or especially the B vitamins that, were water soluble. There aren't much storage for it other than B12, which gets recycled by the liver. But it's within a couple months, you're already going to start getting severe symptoms of deficiency. So we need to continuously get from diet. So what happens to the system is, for example, if you're maybe suboptimal on the amount of calories you're getting, the body starts breaking things down to get the energy. So you'll start breaking muscle, you're losing muscle mass, or you might not have enough amino acids to make certain neurotransmitters like dopamine or serotonin, which then affects your cognitive ability and your mental health. And it's like everything in the body, or your gut microbiome won't survive. So the beneficial microbes population will start dying down, and the pathogenic, the dangerous population will start growing because they're thriving in that environment. So then you don't get as many neurotransmitters being made by the gut for the gut-brain axis, and it's all interrelated. You don't have enough iron to carry oxygen, to make ATP, to make energy. The cascade of events that start are invisible. Okay. So nutrition is really an invisible consequence. We don't see it. People, hair starts falling out. You don't realize it's iodine deficiency, for example. You feel a bit fatigued. You don't know if it's iron. Your brain fog. Like it might be that your zinc status is low, or you keep getting sick. So it might be zinc. It might be vitamin D, which are both important for your immune systems. Right? Or you get sick and you have this chronic low level inflammation because you don't have enough of the vitamins and minerals to help resolve inflammation, which is an important component of our innate immune system. So it's invisible, but the best example I can give would be, let's say, calcium and vitamin D. They're top two priority nutrients, right, in the population. Calcium is, needed for muscle contraction. Our body needs it every day. If we don't get it from diet, it will take from our bones. It's a great storage in the body. And over time, as you're not getting enough calcium in the diet, it starts leaching from your bones and they get more and more porous. It might take 40, 50, even 60 years so that the bone density goes down enough that when you fall, you break. And perhaps, data shows that if most people in older age, if they break a hip, they die within a year. So the consequence, you don't see it. It's not like a broken arm that you go get fixed or a laceration that you heal. Nutrition, when it's happening inside, it's invisible. You can't see it. So it's really not overt. There's many different symptoms and it's non-specific unless, of course, you're getting that consultation with a nutritional professional to assess intake and then say perhaps where some of the symptoms could be manifesting from. So it's really invisible. And that's why it's so important that we educate and empower people to realize that, there's so much misinformation out there on people selling pills and diets and powders, and food industry is so evil. But here, buy my powder, and my collagen and my protein and my vitamin supplements. It's
and
like
exaggerated by TikTok trends, nutrition TikTok trends and stuff like that.
Yes, it's such a mismatch of, yes, there is a role for supplements in the diet 100%, given there's so many shortfalls. But remembering what I said about whole foods and nutrition, if we can get that whole food benefit, sometimes it's more powerful, right, than just fixing. Vitamins and minerals are called micronutrients because we need it in very small amounts, like milligrams, micrograms, and like carbohydrate, you might need 200 grams, or food, we eat like a kilo and a half a day. The micronutrients are micro, just tiny little bits. And what that means is that if you have too much of one, it can also cause an imbalance, and it can become oxidative, or it can become toxic, or it can accumulate in the body and be more damaging. So it's a fine balance. And hence, when you supplement, it's got to be strategically supplemented to ensure that there's no consequence that is negative from the supplementation, and that you actually need those specific nutrients. They're not going to interact with drugs you're taking. They're not going to interact with other things in your diet.
Okay.
Yeah.
Flavia, you published on nutrition's role in cognitive function and mental health. What are the mechanisms linking dietary quality to things like decision-making, sustained concentration, and psychological resilience?
So a lot of the evidence on nutrition and mental health is looking from an angle of prevention. So nutritional psychiatry was a field that didn't even exist, I think a decade ago. And now it's very well, there's clinical guidelines on diet for mental health, anxiety, depression, and so on. So there's a very strong link, the importance of it. But when you're looking at your questions like resilience, cognitive function, there are so many ways in which diet affect that, from omega-3s, right, being necessary. It's one of the biggest proportion of fat in the brain is your long-chain omega-3s, or your DHA. So that's important for the brain to function at its maximum, ensuring that you have the right vitamins and minerals as cofactors to absorb the glucose into the brain cells, for the mitochondria to be able to produce ATP or energy. Like it's everywhere. But in terms of where I've published in and where there's a lot of science is the gut modulation, right? That our gut microbiome not only produce certain vitamins, but it also produces short chain fatty acids, which are compounds, can then be turned into neurotransmitters that can communicate with the brain and impact our brain function. But it also communicates with our immune system as well. So we call it the BIGS axis, right? It's brain, immune, gut, and skin, which are all interrelated and very relevant for the space environment as well.
Yeah. So Food IQ Global, your company, was built on the principle that nutrition information should be backed by science rather than trends. In a field where a new diet goes viral every month, like I just said, what does regular science translation actually look like in practice? And where does the public discourse get it most wrong?
It's a good question. So Food IQ was founded to bring back science to food, right? So that we help organizations from the food industry to NGOs to government to elevate science, because we need to elevate food and nutrition science to have an impact on human health and help people eat better and get these benefits that I'm talking about that are so powerful from our diet. Now, we are in an era that is really interesting. Like when, I'm 25 years as a nutrition scientist. At the start of my career, we didn't even have social media. There weren't even mobile phones were just coming out. Where, I got all my information from magazines. Now it's like this. Before you had to buy it, read it, it's just such a change. But what happened in this is the credibility of experts. So anyone nowadays can have an opinion. And food is really the one thing that everyone feels like they have an opinion that's credible, right? Because we all eat. Yeah. So I wouldn't give advice, legal advice to you, Omar. I wouldn't give, I wouldn't do arm surgery, like orthopedic surgery on you. But for some reason, people feel like nutrition advice, they're all qualified. because they read it on the internet or they read papers or did their research. Like people that say, I've done my research, like you actually don't know how research works and how science works. So really it's a tricky era because there's a distrust in actual experts. When I was studying, you had to be an expert to publish a book, to get on a podcast, wasn't podcast, but to get in a TV interview or whatever it is. Now anyone can, and I think that's part of the issue of misinformation, that there's so much information, and what people need now are skills to determine what is credible and what's not. So critical thinking skills, reflection. And in the era of AI, I believe it's one of the most important skills that we will have is to be able to assess the validity of the information that you're being given.
True.
So it's a very tricky era for misinformation because there's just so much out there. And I think for anyone, it's important to check who's this doctor? Are they a nutrition scientist or are they just like a doctor in another field that has nothing to do with nutrition, giving you nutrition advice? So there's even that element, right? It's not like check your sources.
Yeah.
Yeah. And of course, I think it's great that people have access to information. I think it's so good. Even as a researcher now, it's so much easier. I remember going to the library and indexing journals, finding it, going and grabbing it, photocopying the actual research paper. Like imagine the time saving now that we have with technology, right, in research. So it's very positive from a scientific advancement and rate that we are advancing. But for regular listener, for a consumer that doesn't know what to eat because we're not taught in schools, it's really around put your critical hat on, go who's saying this, what are their qualifications before you just take in information as gospel.
Great. Okay, so let's take the psychological picture you just described and physiological also picture you just described and put it in microgravity. Astronauts lose 1 to 2% of their bone mineral density per month on the International Space Station. What's actually driving that at the nutritional level? Is it the calcium metabolism, vitamin D pathways, sodium interactions, or something more systematic?
Yeah, so it's really a physiological effect of being in microgravity because it's not weight bearing. So when we're on Earth and we have gravity, there are two main predictors of bone mass density. So when I was talking about how we're losing calcium in our bones, if we don't put it back, it becomes porous. That happens over a lifetime on Earth. But as you mentioned, you take away gravity, it happens a lot quicker because there's not that weight bearing stimulates the osteoblasts to build bone, right? So it's not only having the calcium, but you need the mechanical stimulation, which we get when in gravity. You take that away, the body's so smart, our body is so smart that it adapts. It goes, well, I don't need this dense thing here that's metabolically costing me lots of energy to keep alive. Let's get rid of it. So all that calcium leaches into the blood. Right? So it's a countermeasure. There's lots of different countermeasures from a nutritional perspective, like keeping sodium down in the diet, but also ensuring there's enough vitamin D in the diet to help with the intestinal calcium absorption as well from what they're consuming in their diet. So you need to ensure there's enough to put back in the bone because it's releasing that calcium so quickly, but also keeping the sodium levels down because it also excretes the calcium from the. So it's a real, and of course, nutrition is not the only countermeasure. Their resistance, exercise, right? Yes. Training is also important because it stimulates those osteoblasts. And together, research has shown, which is really interesting, the power of nutrition. So astronauts, because there's no, of course, UV exposure like on Earth, we make vitamin D predominantly from UV exposure in our skin. We get very little from diet. There's only a few foods like fatty fish, some chicken skin, a little bit in chicken, a tiny little bit fortified in margarine and naturally in butter. And then also UV exposed mushrooms, which we'll talk about, I'm sure, later. Yeah. So very few food sources. So it's the only like provisional mandatory supplement by default that every astronaut needs to get because there's no way they're going to make vitamin D. So the recommended intake used to be about 400 international units. And astronauts still continue to come back to Earth and lose their bone mass density. But once it got up to 800 international units, and now it's 1,000, with the exercise and the proper vitamin D and calcium and nutrition, they don't have the bone loss that they used to. So it's really powerful how nutrition can add that extra layer of countermeasure. It can both be a cause and a countermeasure. So not getting enough. So if vitamin D status was low, it accelerated the bone loss. But if it was adequate, it prevented it from. So it doesn't cure it, but it's a contributing factor that accelerates the bone loss.
Cool. So speaking about vitamin D, let's now talk delivery. On Earth, if someone is vitamin D deficient, we tell them to get more sunlight or take a supplement. In a sealed spacecraft with no natural UV exposure and a 3-year shelf life constraint, that's if like at best case scenario on these stored supplements, neither of those options can scale. What does that constraint force you to rethink about how we deliver vitamin D to astronauts?
Exactly. It's so exciting, right? So that's before I got into the space sector, I was a nutrition scientist for 20 years, right? So I came in from that angle. I did the space studies program at International Space University. I had been researching mushrooms for the previous 5 years prior to that, their nutrition and health benefits. And one of the unique things about mushrooms is that they're fungi. They sit in their own unique biological kingdom, separate to animals, as humans, and other animals we eat as well, and plants. So typically, if it's going to be diet, you're going to have to get it from animals, because that's the animals convert as well, the UV into vitamin D, and then we eat the animal and we get the vitamin D. But of course, it's going to be, especially for the long duration missions, almost impossible to get the recommended daily intake just from diet. It's basically impossible unless you're consuming 100 grams of UV exposed mushrooms that have the equivalent vitamin D content as a low grade vitamin D pill, the 1,000 international units, which is what in LEO astronauts are currently given. So that's where I went, oh my goodness, like mushrooms are just the ultimate space crop from a nutrition perspective. And then when you start looking at all the other requirements for space crops, for all the plants that have been grown in the ISS, you know, they grow in small spaces, they're a pick and eat crop. They also have a circular agriculture, so they can be grown from almost anything that contains carbon. They're decomposers, they help purify the air. Like the list went on, right? So that's how I think potentially we can solve that problem, is to grow mushrooms and then have a UV lamp or UV exposure. It could be even outside the spacecraft, bringing the UV into the mushroom farm. And because it's only, 100 grams is like 3 to 5 button mushrooms. It's not a lot. They can be eaten raw. Hopefully by then we have some cooking facilities in space. But it not only has the vitamin D, but mushrooms uniquely have a lot of B vitamins. And the B vitamins are the ones that degrade very quickly in the food supply. There's lots of research from NASA on all the vitamins that just sitting at ambient temperature, these vitamins degrade very quickly, right? Vitamin C is a big one. Thiamin's a big one. Folate, riboflavin. They're just like...
Plus exposure to radiation, right?
Exactly. And we don't even know that, right? Because we're doing analysis just in LEO. We're not sending it to Mars. Like we should. There should be research where we send food supply to Mars and back and then analyze the nutritional content. Right? We don't have enough data on the nutritional composition of the food system when it's being stored for a long time. What we know from Earth is that they degrade when they're irradiated, they degrade when they're stored. The best technique really is refrigeration, especially for those water-soluble vitamins that you look at the vitamin, it degrades. Like riboflavin especially is sensitive to light. So as soon as you open something and light gets in it, it starts degrading. And vitamin C is another one. So we've got to be thinking food system and how all those vitamins and minerals degrade, and also how it tastes. Because as soon as it starts degrading, you start getting off colors, off flavors. And if food doesn't look amazing to eat, even high-performing astronauts are not going to eat it.
Yeah, actually, this is a question I wanted to ask you. Astronauts consistently report that food tastes bland in space, which compounds when they're also on low-sodium diets for bone health, right? What's happening to the taste and smell perceptions in microgravity, and how does that alter nutritional intake behavior?
Yeah, so it has a huge impact. So if you think about when you have a cold and your nose is totally stuffy, or anyone that had COVID and lost their taste, it's just sucks. Right? Like food, it doesn't make you want to eat it, especially if you can't smell it very well and if you can't taste it very well. So one of the obvious things that happens because of the lack of gravity, you get the fluid shift to the head. So you do feel like you've got a cold, right? And some people get it, some people don't get it as bad. There's variation between astronauts, right? But the other element is the higher CO2, lower humidity, temperature, noise. Noise affects food intake as well. And like on the ISS is noisy. Yeah. It's like dinging, there's equipment. Like when you think about eating at a beautiful restaurant that's quiet with dim lighting, with someone you love, and then eating like in one of those food courts, cafeteria, it's a different experience, right?
The ISS also doesn't smell the best also.
And then the smell, like they're not showering, like people are stinky, you're wearing the same clothes, like there's an element of it. It's like it's when you're like, look at those beautiful dresses. Women look so gorgeous, but everyone stunk, right? Exactly. That's why perfume was invented in France or wherever it was. Yeah. So there's that, like food system and nutrition needs to take that into account. It's not just let's provide a nutritious food. 100%. That's the number one requirement in space nutrition is the provision of nutrition. But then all the other elements of food, that social aspect, the palatability. So astronauts lose a lot of their taste in space. One of the key ones that it's rudimentary research still. It's so young. We haven't really done enough. There's Australian researchers looking at that as well in analog missions and laboratory setting, mimicking space. But basically all like salt, sweet, they all seem to be dampened. That's why, I don't know if you ever see videos on the ISS, there's like 10 bottles of condiments and seasoning and chili. Because it's to make it taste better, right? Yeah. But that's, again, another reason why mushrooms are so cool, because mushrooms have natural glutamates. It's like natural MSG that enhances the flavor of food. But also from a nutritional countermeasure, it lowers the amount of sodium you need to add without affecting palatability. Okay. So there is research on Earth where, let's say, you reduce by 25% the sodium content of a meal and add mushrooms to it for that natural glutamate umami taste, which is the fifth basic taste. And it's 25% less salt, and people don't taste that there's 25% less salt. So that's powerful. That's really another reason why I said, oh my goodness, mushrooms are perfect for this space. And umami seems to be one of the tastes that's more well retained, not only in space, but in space-like environments like airplanes. Okay. That's why people love a Bloody Mary when they're flying, or wine tastes. Yeah, so you've got that, lower humidity, you've got a bit of pressurization, right? That happens, that all impacts our taste, the noise in an airplane. So it's similar when we travel and we're in an airplane to being in a space station. So there's a nice kind of Earth analog there on sensory aspects of food. So it's really important, because what happens when an astronaut underconsumes calories? I mentioned the body starts breaking things down. It goes into a catabolic state where it's just going to destroy what it has to get the nutrients it needs. It still needs the neurons for you to think and for the body to work and keep the heart rate beating, So it goes, well, I'm going to break down muscle and get the amino acids I need, or I'm going to break down the bone and get the calcium I need. So it's really interesting, because if astronauts underconsume, those effects start happening, but it's hard to pinpoint. A lot of space medicine studies are confounded by nutrition, because we're not measuring that level of suboptimal intake. We're not measuring that level that happens at the individual, where someone might need more folate genetically than another person, and their food choices, because it's really, there's the one thing they have autonomy for is what they eat. Okay. And you don't want to take that away from astronauts, right? No. So as we go to Mars, it will have to be taken away, because we probably won't have the variety and the pantry and the food choices, like the 200 meals that we have on the ISS to choose from. So it's really a red risk, for long duration missions, even on the moon. Nutrition is a huge red risk, and the food system is a red risk, because we just don't have it. It doesn't exist. And that's why I'm in space nutrition, because it's so exciting. Because if we can figure that out, we can figure out how to feed the 10 people on Mars, then we can take that exact same food system and bring it back to Earth to feed 10 billion in a way that's nutritious, right? Because you can't ignore nutrition, and sustainable because it's a closed food system that takes into account the air, the waste, everything is interlinked. And that's what we need here in disaster regions, in the middle of remote cities, in places where we know on Earth people are under-consuming their nutrition.
Flavia, there's growing concern about gut microbiome disruptions during spaceflight. Changes in microbial diversity, immune dysregulation, altered nutrient absorption. Can you unpack how the gut immune axis we just talked about earlier is affected in the space environment? And what role dietary composition plays in stabilizing it?
Well, we don't know. So this is just new evidence that's emerging. That is that, gut dysbiosis really in space. So it's really, we don't know why. I have some theories around it. Of course, you need a lower residue diet in space, because if someone's about to do an EVA, you don't want them farting in the spacesuits, for example. You don't want any big gut discomfort, which is basically how you feed your gut microbiome. It's plant material, undigestible, like plant fiber, right? And the space diet, the astronaut diet, isn't very high in fresh vegetables. It's not high in the food that feeds our gut microbiome. So, of course, that probably has a huge impact, right? It's all prepackaged, thermostabilized food. Very little fresh food delivery for fruits and vegetables that astronauts get is only every now probably 3 months or more as the ISS is being decommissioned. So it's really interesting because it's probably diet that plays a role, but it's probably everything, right? It's the lack of sleep, it's the lifestyle medicine, circadian rhythm being disrupted, the isolation, everything that impacts our gut. And also what's really interesting too is the air. Right. So the air in a space station is highly filtered. It's where we come from the lens of like any microbe is bad. So we've got to make sure that we get rid of all of that bad microbe. But on Earth, like people go into nature, there's loads of compounds in air and microbes in air that are known to seed our gut microbiome as well. Cool. So if you're in this environment where you're not breathing any of these plant compounds or fungi or bacteria that's airborne, then if it's going to affect your gut, and it's going to affect your immune system, and you get that dysbiosis of the levels of beneficial versus non-beneficial microbiota that exists. So yeah.
No, sorry.
No. So I think it's lots of different elements, but I think the air, the lack of beneficial microbes in the environment as well, as much as the diet, definitely play a significant role in the gut dysbiosis alongside everything else, right? It's the stress, it's the lack of social connection with family and friends, and it is just the lack of sleep. It's just, we're all interconnected. There's not one thing. The human body is a complex system.
Okay, so let's kind of put everything together and have a thought experiment. On Earth, psychological distress from food monotony is a discomfort. But on a 900-day transit mission to Mars, the crew of 4 is confined in a habitat. So menu fatigue becomes an operational risk. It affects caloric intake, morale, and crew cohesion, I think. How do you design...
Resilience, everything, yeah.
Do you design a nutritional strategy that accounts for the psychological dimension when your ingredient list is fundamentally limited by mass and volume budgets?
Yeah, so my big flag in space nutrition is treat nutrition the same way as you would treat fuel for the spacecraft. We can't prioritize engineering and not prioritize humans that are going to be in the engineered spacecraft.
Here.
Right? So right now it's always mass, volume, what's the minimum nutritional? So we're kind of reverting to the end of deficiency, right? Rather than optimal health. And realizing, like you said, we don't know so food's going to have to be provisioned We don't know the crew that's going to go. We don't know what culture they're from. So there'll be probably no room or volume for the preference foods that are about a quarter of the intake on the ISS. There's just, we don't know how, like there is just no way, like right now you can envision that impossible food system, but I know that we can make it happen. And one way is to really prioritize food to the same extent in the hierarchy as you would fuel.
Okay.
You know, which then gives more allowance for more food because it does provide that resilience, that sense of autonomy, that cultural connection. There's just a million evidence-based published reasons that food is more than nutrition. Right? Just like on Earth, you know, if someone's isolated, if they're like the military is a great example of submarines, it's super important for morale and one example I can give, it's a really cool story. When I was doing my PhD, I contributed to a paper called the Food Lifeboat. So what do we have to have in our home to provide all the nutrition we need in case of a pandemic or a catastrophe? So this was back in like 2005. Really cool, like ahead of its time, right? And I remember, just to put into context, having discussion with the other researchers, Professor Stuart Trussell and I were on the chocolate camp. We need chocolate in the food system here. And everyone else is like, no, because then you're not going to get enough vitamin C and you're not going to get, and we're like, but it's a pandemic. It's a catastrophe.
Yeah.
Chocolate tastes good and it makes you feel good. And we've got to allow calories for chocolate and compromise something else, right? So even back, 20 years ago, it's that prioritization that food is more than nutrition is just as important as well. So ensuring that you have the comfort foods, that we're not just looking from, of course, we've got to optimize nutrition, but we also have to optimize well-being that food brings, right? So put the chocolate, let's send some chocolate to Mars. It might have some taste changes. It depends on the quality of the chocolate, but we need it because it's so important for that mental resilience and sense of well-being and connection to Earth and culture and people.
I'm sure a lot of potential astronauts now are like going thumbs up. You spoke about submarines. How does the nutritional challenge of long duration spaceflight compared to other extreme confinement scenarios you're aware of, like the Antarctic winter over stations, submarine deployments, or even ICU patients? Are we dealing with the same physiological cascades, or is spaceflight nutritionally unique?
Yeah, it's basically the same thing, as just space is louder and more accelerated. Right? So a couple months in space is the same as accelerated aging on Earth. So what's really cool about doing space nutrition research is that we get to discover things that we might otherwise not be obvious on Earth, or that it might take years for it to develop. Right? So it's really submarines, ICU, and hospitals. They're analogs for the space environment, but doing research in space allows us to fast track that. So there's lots of different examples, but I mean, the drug for osteoporosis was discovered thanks to space. And now it's used in every, case of osteoporosis to reduce the bone loss that happens. There's a real, and nutrition being such a young field, there's so much that we still need to discover. Like, does the higher radiation beyond LEO, even the radiation in LEO, mean that you actually need more folate or more of the B vitamins in the one carbon metabolism? There seems to be that by getting enough B vitamins in that one carbon metabolism, this is Scott Smith's work, and I'm so excited because there's a trial going right now to go, it might actually be a contributing factor with interacting with genetics that results in SENS, the ocular syndrome, space-associated neuroocular syndrome, which no one really knows. Is it the pressure because of the fluid shift? Like, what really causes SENS? No one knows, and only some astronauts get it. And there seems to be a clear potential mechanism that interacts between inadequate B status and a genetic polymorphism, or a SNP, a variation in the gene, in that one carbon metabolism that predisposes someone to get it. Like, it's amazing. It's something that otherwise would not have discovered, that B vitamins potentially have such a direct link to ocular health. And also potentially even vitamin D and ocular health as well is another area. So It's really, nutrition science is so young, and space makes everything that happens in the human body just a bit louder, more obvious, and faster. So we need less time to see an effect, which is very exciting. A new area that I'm really passionate about is like your herbs and spices and the color compounds in fruits and vegetables, and the power that those compounds have on health, and to be able to test that in the space environment. Yeah.
In March of 2025, your team flew Oyster mushrooms on SpaceX's Fram2 mission, the first human spaceflight over Earth's polar regions, and critically, the first attempt to cultivate mushrooms as a crop in space. Not just mycelial growth, which has been studied before, but actually fruiting. This was the Mission MushVroom with a V, and it was assembled in what your co-investigator Ralph Fritzsche described as an insanely fast turnaround. Take us inside the science case first. What made oyster mushrooms, especially Pleurotus ostreatus, am I saying it right?
Yes.
The right organism to
Pleurotus
test.
ostreatus.
What made it the right organism to test, and what were the primary scientific hypotheses you were designing to evaluate?
Well, really, I was shocked that we didn't have a mushroom cultivation system on the ISS yet, right?
Mm-hmm.
So it was really, we needed as food. I came in as a nutrition scientist and, you know, as like, it's an ultimate crop when it comes to nutrition, because not only does it have the ability to make vitamin D, as we mentioned, but it has nutrients, like the really high amounts, more than a quarter of daily intake of some B vitamins, potassium, but then you also have selenium and copper, which are not typically found in plants in high amounts. Mm-hmm. So it really has like nutrients found across food groups, in addition to really cool bioactives that are powerful, like ergothioneine. So ergothioneine is a sulfur-containing amino acid, so a building block of protein, that has a very powerful antioxidant and immune-modulating properties. Now, it's not like the vitamins and minerals that we have a recommended daily intake, but we have specific receptors in the human body for ergothioneine. Mm-hmm. And the largest source in the diet is mushrooms. The next source like blows it out of the water. I think it's black beans, but it's like the difference is huge. So it's really the only place we get enough ergothioneine in a diet would be mushrooms, consuming mushrooms. And so there's from a nutritional perspective, all mushrooms have that in different amounts. And oyster mushrooms, why they're chosen as the ultimate space crop is because they have very high resilience in their tolerance for dew levels, for humidity, for temperature. So given the variability in the space environment that we know with respect to those markers, it's a great crop. The other reason is that it can grow from almost anything. Oyster mushrooms are decomposers, like you say, growing on logs in the forest. Mm-hmm. NASA has shown, just published just before our mission, was really exciting, growing from inedible plant waste and also used cotton t-shirts. So the idea is like, hey, let's recycle some waste in space and grow oyster mushrooms from that. So instead of like, what are you going to do with the clothing on the Mars mission, perhaps, right? Yeah. It's going to take up room, and maybe we can grow mushrooms from the t-shirt that's just not cutting it anymore. So that's the idea. Oyster is like a very resilient, nutritious crop that can grow, and it grows relatively quickly, like most mushrooms. Mm-hmm. So the end-to-end life cycle is really, around 40 days, 45 days. Mm-hmm. So from the very start of the initiation process of the growing all the way to the end. And basically, I had just presented at the International Astronautical Congress my paper on why mushrooms are the ultimate space crop. And then through the membership of the Space Industry Association of Australia, there was an opportunity for an expression of interest for a mission, for an experiment that had a certain constraints. And I responded to that EOI and said, well, we can attempt to grow mushrooms, right? Oyster mushrooms. And we won the EOI, but we came into the mission because someone pulled out. So we got notified that we got on the mission in November 2024. And being based in Australia, if anyone knows Australia, it's like Europe in summer. So January, everyone thinks shuts down. It's like August in Europe, or July, I guess, in the US. So we really didn't have a lot of time to figure out the hardware, which was due yesterday, the mechanism, and how we were going to do it all. So, and that's what's exciting, because this is new space, right?
Yeah.
The traditional research pathways that used to exist to do space research have changed.
Yeah.
So it's an opportunity for a company, independent company, to do this. We all have affiliations with universities as well, but we did it independently of that typical space pathway to do research, which is very exciting for the future of space nutrition and space nutrition research. So we were constrained with, of course, mass and volume, like most experiments. So what we sent was a substrate block. So substrate is it's usually a grain with the spawn, which is like basically the seed of the mushroom. With dust, sawdust and wood chips, and it's really like the soil for plants. And then the mycelium is the fungus, is the actual organism, and it's like a white network. And if you see it in the forest, it's all underground. It connects all really plants and living things. It's pretty epic. And then the mushroom is the fruit that comes out when it replicates. So it opens up its gills and releases spores. And it grow more mushrooms. So one of the reasons mushrooms haven't really been explored as a space crop is probably the risk of spores, because spores are like the seeds. They can lodge in spacecraft, and then all of a sudden you've got oyster mushrooms popping out of the, Dragon capsule in a few years. So it hasn't really been explored, I think, because of that fear of inhalation of the spores and potentially, contamination. Because on the Mir space station, there was low order fungus. So your yeast mushrooms are like higher order fungus and growing, right, on the space station.
Okay.
So we know that they're very resilient to that space environment. And really, so we sent this block with the substrate and the mycelium fully colonized. And basically, the way we control the environment was with putting it in a bag, with filter for gas exchange. And then we also sent Falcon tubes, which is your centrifuge tube, like your lab tubes for those that aren't in the science, with the substrate and the beginning of the colonization of the mycelium on the substrate to see does it continue to colonize, and then to do microscopy and look and see how's the hyphae and the branching of the mycelium in space. And then with the block is to see, can it start fruiting in just a 3.5-day mission?
Okay.
And basically it was successful. So even though it was the most non-controlled, it was like foundational experiment to see, will it grow? Can we use it as a potential crop? And it did. So we ended up sending sporeless. There was a sporeless variety that we had access to. So we sent sporeless, which takes a little bit longer to grow. It didn't mature into a full mushroom, but we got the beginning of the fruiting of the mushroom in the block. And we got the colonization, and then we did nutritional analysis of both. And there didn't seem to be any nutritional differences between the space and ground controls. And there were some differences in the branching, but the hyphae grew the same way as the ground controls. But there seemed to be a bit of a difference in the look of how it branched out. We got new growth. It was very exciting, because even in the most non-controlled condition, the fungus still grew and colonized and thrived. Like, it's amazing.
It is amazing.
So
is it because the gravity, lack of gravity or microgravity, there was a difference in the growth, or?
Well, we don't know, right?
We don't know. Yeah. Okay.
We don't know if it's
for future scientists to figure out.
Exactly. Now that's foundational. A next step is really we want to develop a autonomous mushroom growing chamber where you control the humidity, etc. Now, the issue with mushrooms is that they're just like us humans, that they need oxygen and produce CO2. But that's the beauty of them, unlike plants, that they don't need gravity to grow, right? So there are plants that don't need it to, but they go to where the oxygen is, where their nutrition is. And you can also fortify. There's some research where oyster mushrooms have been fortified. Researchers in Brazil doing this, adding selenium to the substrate, and mushrooms take up the selenium. So there's different pathways to not only provide nutrition that you might not be able to get in a supplement in long duration missions or deep space, but there's technology level is really low, right? For crops and being a source of nutrition. We're really far from relying on it. Right now, where it could add value is to have some plants and fungi growing in the spacecraft to provide more of that connection to nature, connection to Earth, giving them something to do that makes them feel good, and potentially having some harvest and food from it. But it's unlikely in 10 years' time even to provide reliable nutrition to astronauts.
Yeah. So
Yeah.
the Fram2 mission was 3 to 5 days long and carried 22 experiments. Your mushroom experiment was reportedly conducted on the last day of the mission, right? With the contained box that you said, which housed the substrate blocks and the tubes. What were the hardest design constraints you had to work within? Is it size, the power that you require, crew time, contamination control? Which one shaped the most?
Which one? Probably the volume and mass restriction, right? Because it meant that we couldn't, and the time constraint of the mission. So we couldn't develop a better system because it hadn't been done. There's no like off the shelf space hardware to grow mushrooms like veggie, you know? So we had to really, with the time we had, developed the best experiment we could with the mass and volume constraints we had and the crew time we had. So it's all just like the other 21 experiments there, we're all limited based on all those things. And given it was a biological experiment, the mass and volume, of course, has a huge impact. In terms of the crew time, you know, Eric Phillips and I believe Rabea also was with him doing it, but he was in charge of doing the observation for us. So he took photos and videos of each Falcon 2, pulled it out, looked at it, you know, and described what he saw on day 3 as well. And then when it splashed down, we went straight to the laboratory, did some microscopy, then sent the samples for nutritionals and for further microscopy as well.
Cool. You had also a ground control running simultaneously, right? In the post-flight analysis, what are you specifically comparing between the space-grown and the Earth-grown samples? And have you seen any preliminary differences in the physical, biochemical, or genetic data that surprised you?
Yeah, so genetics, we didn't get a chance to do any, but we did look at, we might still, because we still have the samples frozen. Like I mentioned before, there was the hyphae, you know, continue to grow perfectly. Nutritionally, there wasn't any statistical difference. Sample size is, of course, very low. And what's interesting was that structure that we're seeing. So there was visual differences between ground and space, and there's more to come here. I'm actually presenting this research on a Fram2 research day next month in Oslo.
Cool.
Yeah.
So
yeah.
On the mushroom mission, how does what you observed map against what you predicted?
Well, we predicted that it would probably continue to grow, given, you know, mycelium can grow so well in a space environment. And there were other biological experiments where mushrooms were attempted to grow, just not as a crop, but it was limited. I believe there's 2 others. And so predicted that it probably would continue to grow. We weren't sure in the environment that they were in, if they would. So I would say the most surprising finding is, despite not having adequate real protection from the vibration on launch, for the lack of continuous oxygen supply and you know, humidity control, it's still attempted to fruit. It's a very resilient organism, which I guess confirms that it is a new space crop that we want to investigate further, because it has proven to be quite resilient. Yeah, and we want to see if differences that we've observed in the small sample size what does that mean, right? I guess for growth, for nutrition, because there's lots of space crop readiness, things we have to tick, like fungal safety system, like creating a growing chamber for fungi that's different to plants. And then, of course, safety and toxicity studies, looking at, can we eat them? Because even though there's been lots of crops grown in space, very few have been eaten, right?
So the lettuce in space haven't been eaten?
I think there's only 2, lettuce and I can't remember, maybe radish. I can't remember. There's only been a couple crops that are actually being eaten.
Okay.
Because there's a lot that you need to do before you get to that stage. So as I mentioned, you know, space crop research from a provision of nutrition, it's still in its infancy.
Okay. I spoke with Ralph Ritchie, your co-investigator and former NASA space crop production manager. And he described Mission MushVroom as a case study in the power of networks. An Australian researcher, a Cambridge PhD student, and a NASA veteran assembling in weeks to get the science on a private mission. From your perspective as a principal investigator, what made that collaboration actually work across those time zones, institutions, and expertise domain? And what would you do differently next time?
What worked really well was that I think we're all purpose-driven individuals. Like we all do what we do because we see the bigger purpose and picture of why we're doing this. We're all very passionate about space and passionate about food. And what was really interesting about our mission is that we got like 1.5 billion reach with our media release about it. And I think it's just that food makes space relevant. Because everyone can relate when you're talking about satellites or whatever, like it's so distant for people, but food is like, oh, I get it. I eat mushrooms, you know, it makes space relevant. So it was around having that, probably our ways of working that are very similar, being purpose driven. And it's really, from my perspective, as a PI, you're the master coordinator, right? Of the risks, the project, the milestones, what we need to achieve, how we're going to achieve it. It was a lot of work. I mean, it took a lot of time and, you know, dedicated to figuring things out. And it was one problem after another that you're troubleshooting. What would I do differently? Maybe not agree to that such a short timeline. But you have to, right?
We're like, of course, this is once in a lifetime, right?
Like, and I remember with Ralph, we'd be laughing about it because Ralph, of course, being NASA and having all that experience for so many years, it was great because we balanced each other. Because I had the like, of course we can do it, and he's like, once I see it fly, I will believe it, right? So I had the can-do attitude, but he had the devil's advocate attitude along the way. And of course, with Annie, you know, being so knowledgeable about the mushroom cultivation and growing and being able to have, you know, sending her stuff so she can set up the flight testing, the ground testing before flights. It was really around, it was international collaboration. And I must say what made it successful was everyone's willingness to help each other. And that's one thing that I love about the space sector. Everyone is so nice and willing to help, you know. So Jamie Foster at the Australia's Institute, the University of Florida, gave her lab space to be able to set up her experiment and do it. Like it was just, everyone was just super helpful. And I think it was a collective effort of making it happen, but also that purpose and belief that we can. So I tell a lot of people, you know, that space makes the impossible possible. And the reason it does is because it adds constraints. It adds those constraints, and what we had was a size constraint, volume and mass, but also time.
Time, yeah.
And that's how we innovate, right? So, and the key thing that I've learned in my life doing things that are quite innovative and seem impossible is to focus on the what. A lot of people fail because they focus on the how. And I didn't know, like leading up to this mission, I didn't know how I was going to send mushrooms to space. And if you stop thinking about the what and focusing on what you want, because the how, you can't imagine it. You know, there's no way I would have imagined to get on the SpaceX Fram2 mission the way we did, how quickly we did. You just can't imagine it. So I think it's, you know, my tip is to work on really focusing on the what, and then the path starts presenting itself on the how. So I think it's also not being too focused on the nitty gritty when you're wanting something. Focus on the how, and the next what, we're focusing on is that autonomous growing chamber.
Cool.
And figuring out how we could create that.
Flavia, you've demonstrated that mushrooms can convert waste substrates into nutritious, palatable food in a contained environment with the spent substrate usable as filterizer, effectively closing a bioregenerative loop in a sense. If that closed loop model validates at scale, what does it actually change about how we approach food production here on Earth? Not as an analog, but as a directly transferable technology.
Well, so I didn't demonstrate that, but NASA did. And And because I'm not a plant scientist, or a fungi scientist.
Mm-hmm.
But what I love about that circular agriculture, because even on Earth, mushrooms are grown in a circular agriculture way, right?
Mm-hmm.
There's animal waste that's used to create that substrate and like it's kind of like the fertilizer for mushrooms. And that spent mushroom substrate, when the mushroom growing is done, is used in nurseries, right, as mushroom compost to grow more plants. So even on Earth, there's that circular agriculture that happens. I mean, there's still a long way to figure out how we could mimic that in space.
Mm-hmm.
It might not be substrate, it might be liquid substrate as well,
Mm-hmm.
right, that we're growing mushrooms on. But the opportunity is, and I've spoken to this with mushroom growers here in Australia,
Mm-hmm.
is to think about all the kingdoms of where our food comes from and how we can create this future farm that have fungi, have plant,
Mm-hmm.
have algae, which is the Protista kingdom,
Mm-hmm.
right, and have animal. Because then the animal waste gets fed into growing mushrooms, and then the mushroom one grows plants, and then you're getting the nutrition from the algae feeding into the substrate. Like, we need to be thinking food system
Mm-hmm.
in a food system way. And that's why space is epic, because it forces us to think in a food system closed bioregenerative way. So the next step is to be thinking in space how all the air, the waste, the water are all interacting, not just focusing on food, right? It's how the food system sits within the broader system as well.
Okay. Your priority nutrients research identified 6 population-level critical nutrients for Australia and New Zealand using a novel 4-step methodology. You've also said that methodology is globally applicable. How does the space nutrition framework, where you're forced to think about a nutrient density per gram of payload, inform or sharpen that terrestrial population health work? Do you see the two converging?
Yes, I think 100% the two converge, because right now it's a big problem that people aren't getting enough nutrition. One of the big problems is iodine as well.
Mm-hmm.
So in Australia, there's mandatory fortification of bread with iodine because our soils are really low. So if in space, if we can figure out where iodine can come from in a way that's innovative, we can then apply that from farm to human health, right? Because right now we're fixing the problem at the end of the food supply, rather than figuring out how do we get more iodine in the soil so the plants have more iodine and our foods that we're growing have more iodine.
Mm-hmm.
So I think that space will help figure out that micronutrients shortfall problem from a farm to health perspective, rather than trying to figure it out from a the end point of health, supplementation, food fortification angle. And that's where there's a direct link between space and Earth research.
So you've advocated for an inclusive approach to future food, like conventional, indigenous, synthetic foods, all elevated by the same scientific standards. How do you weigh the trade-offs between those categories when the goal is both nutritional adequacy and environmental sustainability at a global scale?
One of my pet peeves about sustainability arguments on Earth is when they don't take nutrition into account.
Okay, speak more.
And right, so there's a lot, if you look on LinkedIn, there's a lot of posts, a lot of commenting. It's starting to get more momentum now where people are realizing you have to take nutrition into account.
Mm-hmm.
Because if a food is more sustainable, environmentally sustainable, but it's lacking in those priority nutrients, or it's lacking in the nutrition we need, then you're going to have to eat more food to make up for the shortfall of that food that is more sustainable. So that's not more sustainable, because then the carbon footprint of eating more food to get the micronutrients isn't sustainable. So really what I would love to see is that nutrition being part of sustainability metrics on Earth and measuring it adequately from the end to end of nutrition.
Mm-hmm.
And that's why, again, space is perfect, because in the space environment, you can't ignore nutrition.
Yeah, definitely.
Right? Because there's catastrophic consequences.
Mm-hmm.
Whereas on Earth, there isn't. As we've seen, a lot of the population have shortfalls and are deficient. And there's no catastrophic consequence that's overt. But in space, it becomes catastrophic. So I hope that we can leverage the space environment to figure out how to create this more sustainable, nutritious food system on Earth, because it's Spaceship Earth. It's all the same air. Yep. It's all the same water. Like, where does waste go? There's only limited space. Like, we're literally, Spaceship Earth is an analog for the spaceship in Leo. right?
True.
So yeah, people don't realize and that's what it's really nice about the overview effect is that when astronauts go to space and they look back, they realize just how finite our planet is. If we don't take care of, the soils and our water and our air, it's going to have a direct impact on us humans because we're in the same environment. There's no segregation between the type of animals on the planet, the type of plants on the planet. We're all interrelated. Yeah.
You've said that space food research has revolutionized the global food supply and will continue to do so for a population of 10 billion by 2050. Where specifically are you seeing space-derived food innovations gaining traction in the terrestrial systems right now?
Oh, I love this.
Not in theory, but in actual adoption or pilot programs.
There is so much. So I think people don't realize. And that's so I do a keynote on the future of food and what we'll be eating, in 50, 100 years. And when I started, that's what got me into the space sector is because I started realizing, wait a second, space has already shaped our food system today. And what I mean by that is that freeze drying came from the space sector, HACCP, hazard analysis and critical control point, which is the way our global food supply is safe. Is thanks to space. Even making protein out of air was something invented by NASA in the 60s and then shelved. And now it's being reopened and commercialized. Cell cultured meat came from originally a NASA funded research. 3D printing of food. So when you're looking at all of these food futurists talking about the future of food, they all talk about all these exciting technological advancements. They came from space. So not only has space helped us create freeze drying and food that has 80% of the nutrition, but only weighs 20% of the original weight. It's used for disaster relief, for military, camping, and of course in space right now. It's so all that technology that we're going to need to create food that is stable, where the vitamins and minerals don't degrade, where it still tastes good, provides joy, is highly nutritious, whatever this technology is to get us that food system to Mars, is going to be applied on Earth because we need all those technologies, right? It might be even developing the air fryer that the Chinese developed for space. Yeah. There might be some really exciting cooking technology from that we can then apply for making food more nutritious on Earth because we've discovered some different convection system that space allowed us to see that we couldn't see we could do on Earth. It's from a technology perspective, but also from ensuring that the nutrition provision remains for a long duration, which it might be shelf-stable foods that we need as our food supply, becomes less and less abundant. So it's really, I believe that it's going to shape the future. It's already shaped what we have today. And with this new space age that we're in, it's only going to accelerate the rate that we innovate.
Let's go back now to a subject you talked about earlier in our conversation today. On Earth, we inhale a complex mixture of airborne substances like vitamins, fatty acids, trace minerals, beneficial bacteria that your research terms Aeronutrients and Aeromicrobes. So spacecraft air is heavily, as you said, filtered for safety, stripped out of particles and microorganisms, and that's by design, of course. You published work suggest this filtration may have unappreciated health consequences. Walk us through the hypothesis. What are aeronutrients and what evidence supports their biological significance, and why should spacecraft designers care?
Okay, so it's really cool. I hope there's some spacecraft engineers listening. But let me start from the beginning. So basically, Professor Steve Robson and I coined the term aeronutrients because we actually started out of curiosity. We looked at the evidence to go, can we actually absorb nutrients from the air we breathe, right? So traditionally, what's happened with air research is that we've been focused on risk. We've been focused on pollution, and we've been focused on germs of what is bad in air, right? And kind of all the data that exists today, profiling environmental air composition, has that lens of pollution and risk. So we asked the question, well, are there other bioactive compounds in air that could be beneficial? Just looking from another perspective. And surprisingly, we found that yes, there are compounds in air. There are evidence showing that there are vitamins, fatty acids, and minerals in air that is potentially there for us to absorb. So the second question was, can we actually absorb these nutrients from our respiratory airways? And the answer again, yes, borrowed from medicine, right? So not only can we, but it's a highly effective route for drug administration. So when you think of insulin that's administered intranasally, or when you're doing surgery and you get the anesthetic delivered through your mouth to the lungs. So we've got huge amounts of capillaries in our nose, the vascular structure that goes straight into the circulation in the heart. Mm-hmm. And same with the lungs, with all the alveoli, right? And all the vascular volume that we have in the lungs that, again, goes straight into the circulation. Mm-hmm. And we also have the olfactory bulb, which is the only place in the body that is connecting the outside environment to the brain, that bypasses the blood-brain barrier. That's why recreational drugs are so effectively, within minutes, affecting the brain. Mm-hmm. So when you look at the evidence, you go, wow, mechanistically, medicine already uses both pathways to administer drugs. So what evidence exists in nutrition? Now, what's interesting about nutrition is that we've kind of, yes, there are some compounds naturally present in air, might be manganese, iodine, depending on the environment. And the concentration is very low. But we eat about a kilo of food, 1 to 1.5 kilos a day. We breathe 18,000 liters of air. Wow. So the volume of what we're breathing is much higher. But also when we eat food, our stomach has acid and we can absorb large molecules from the gut. So the acid breaks down the protein into amino acids. Everything has to be broken down, carbohydrates into glucose to be absorbed, because we can only absorb things that are size up to 260 Daltons. And when you look at the airways, it's like 160,000 Daltons. I can't remember the exact value, but it's like substantially larger, but also smaller. We can absorb nanoparticles in our respiratory airways. Okay. So the range of bioactive molecules in the air that we can actually take in are much larger than the gut, and it bypasses the liver. So it's called first pass mechanism, where it goes straight into circulation. Wow. Things don't get broken down, so the concentration that it gets absorbed in is much higher than when it gets detoxed by the liver. So physiologically, it's all there. There's precedence from medicine. And when you start looking at the actual evidence for nutrients, we have very strong clinical human evidence, randomized control trials for vitamin B12. It's amazing because nutrition never looked at it that way. It's so interesting. So there's evidence from as early as the 1980s, and it's consistent evidence from different populations, different doses. So in our Aeronutrient therapy paper, so we've got 2 papers published on this topic. The first is going, hey, look at this. And then the second one's we should actually look at this from a medical perspective to give supplemental vitamins to people who need in a metered, regulated dosage. So in those studies on vitamin B12, different populations from children to the elderly, and they all consistently show that there's minimal side effects and it's more effective than taking a pill. Not as effective as injection, but it's another route that's not invasive, right? So it's 10 times more than effective as a pill and 10 times less effective than injection. So it's a different method for therapy. And then there's all this other evidence. So there's toxicity evidence on manganese in welders and copper from tires being neurotoxic to children. And then studies looking at lung disease, where they give them, zinc to see if it improves infection resolution. And they're not measuring blood status, but it's proving that we can absorb all those different micronutrients as well. So there's some evidence also for vitamin D, and there's some evidence which is mostly in animals, but there's also evidence for vitamin A in humans. So it's a whole new area where we're basically going, hey, there's an opportunity here for medical intervention, just like we have for, drugs, insulin, or the drug for heroin overdose is also inhaled for nutrition. And the idea is that maybe we can fix some of those micronutrient deficiencies with air. And that's how I believe it applies directly to the space sector. We might have compressed air with metered dosage of vitamin D, of iodine, of certain nutrients that perhaps we, aren't going to be able to get from food, and there's no solution. And that's why, I go, the impossible, we need to shift our perspective to, like an overview effect, to see the impossible. And we shifted to air to go, hey, is there nutrition in air? Literally. And there is, right? So from a spacecraft environmental perspective, so one of the studies on iodine in children in Ireland, they showed that, so there's air, the currents that pass kelp, beds of kelp, that then the iodine gets aerolized, and there's a high concentration of iodine gas in air when there's a lot of seaweed or kelp near the ocean. So this study looked at children that lived in the high seaweed coastal area, low seaweed coastal area, and rural, and compared atmospheric iodine concentrations, and then did urinary, which is the standard, it's how you measure iodine in the body. It's not a blood test, it's urine, and looked at their urine levels. And there was a direct stepwise correlation between iodine levels in high seaweed areas, which was the highest, urinary levels in children, and the risk of deficiency. So it was like under 10% deficiency rate in the high seaweed, and it was 33% in the rural deficiency rate for iodine. It's environmental, it's an association. You can't say it's causal, but it means we need more research looking at environment and looking at what's in nature that we might need for nutrition. Because I believe that because we haven't looked at air, there are potentially compounds that we only get from air. There are potential nutrients that we don't know are nutrients because we don't ingest them. We inhale them. And we inhale them from our natural environment. So where we're going there with that is that there are many plant compounds that exist in nature. And there's plenty of association studies showing that forest bathing, nature immersion improves depression, anxiety, cognition. It's just people sitting in nature. It's not, doing exercise in nature. It's just sitting in nature, having time with blue space, with green space. And perhaps there's a link there with the beneficial compounds, including the bacteria, right? So that's a whole other area where we know that people that live in rural areas have a more diverse microbiome. They have, because you do get, so through the oral, the mucus clearance, you also swallow and you can see the gut microbiome from air. And also the type of bacteria we have in our nose and lungs mimic in our environment.
Okay.
So Aeromicrobes is a whole other field to investigate. And from a spacecraft design, I believe that the future of the air in spacecrafts will need to consider that we might have to add back in some of these beneficial bacteria.
Yeah. So
that maybe modulate our gut microbiome.
So are you talking
we're taking out?
Are you talking about something like selectively reintroducing specific compounds into filtered air, or is this something more fundamental about how we conceive closed environment atmospheric design, let's say?
It's all speculative, right? But thinking futuristically, big picture, I would say perhaps we would have greenhouses and green rooms and plants where the purpose of that is for those compounds to get into the air system, and that where it might not be filtering everything out in our filtration.
Do we have a classification of what plants produce what into the air as nutrients and microbes and chemicals?
Yeah.
This is exciting.
There is some, so in our first paper, we touch on it slightly. There is some research, but it's completely outside my field of expertise, right? But it is very exciting. My point is we need to work with environmental scientists, air scientists, and nutrition to start mapping air in different environments and what's actually in it, and start looking for compounds, not from the lens of pollution, but from the lens of like, maybe there's stuff here that is beneficial. And there is research. So there's research with plant compounds, I think they're called phytoncides, that have been shown to have physiological benefits. Same with pollen. Pollen has also been shown to have some physiological effects. There's a lot of research in that area. We're working on a third paper on specific compounds in air that maybe aren't nutrients, just to start that conversation and dialogue around, well, what else is in air that we need to be studying and looking at for that physiology, and also mental health for humans. Yeah.
So I've spoken with the space architects about habitat design, air composition, volume, environment controls, and with biomedical researchers about how the space environment affects cellular health and the microbiome and the immune function. Aeronutrient therapy sits at the intersection of all of those. Do you see these evolving beyond space applications into terrestrial medicine, let's say, therapeutic delivery of nutrients or pharmaceutical through controlled inhalation in clinical settings?
That's the reason why we wrote the paper, to go, look, the evidence, at least for B12, is already there. Why aren't we using that as an option over injection, right? So it's around starting to go, we need to have the design of what, I imagine something like an asthma puffer, right? A metered dosage of specific micronutrients tailored to the person's medical need to address the deficiencies and optimize nutrition, where potentially if someone's got irritable bowel disease or they have dysphagia, they can't swallow food properly, or, because right now, if you can't eat and you can't have a gastro tube, it's TPN, it goes straight into the blood. So the other alternatives to get some nutrition that might be feasible, 100%. And there's lots of cases. There's cases for needle phobia. If you need a vitamin B12 injection, or if your diet is inadequate, if you're not consistently taking a supplement and you're vegan, perhaps. There are many applications for aeronutrient therapy on Earth, especially for those vitamins like vitamin D, might be vitamin B12, iodine. Magnesium's another huge shortfall nutrient, that people aren't getting enough, that we could develop and just offer another adjunct therapy option that it's outside the box, literally, right? It's not food, but is an effective strategy to address. So all the B12 studies showed that it could cure pernicious anemia, which is vitamin B12 deficiency. So actually, in the inhalation of B12 or aerolized B12 or intranasal B12, both cured pernicious anemia.
Amazing.
And there's plenty of... It's pretty amazing. We made a table on our paper for those interested in reading more about each study. We even mapped the rate. So it increases more rapidly than the others, but then it pans out. And really the effectiveness is oral, then aero, and then injection.
Okay. Flavia.
It's really interesting.
Yeah, it is. Imagine you're advising the food and nutrition system architecture, let's say for a prominent lunar base, 6 crew rotating annually with a 2035 operational date. You have in-situ crop production, a closed-loop mushroom cultivation system, pre-packaged reserves, and an atmospheric management system informed by aeronutrient research. What's the one nutritional variable or capability gap you'd insist on solving before that base becomes operational? And where does the field need to be by then to solve it?
Wow, so you're talking about a complete food system. I would say... Yeah. The biggest thing is the integration of the different kingdoms.
Okay.
Of where food comes from. Like I mentioned before, I've got this vision for algae, which is protista, fungi, animal, and plant. And figuring out how, and animal, like thinking insects, right? Fast growing, compact, highly nutritious. So I still think we'd have the 4 kingdoms growing on that lunar base to provide the nutrition that we need. And it's the integration that we need to start working on how all those systems come together to provide food. But I guess that's more of an agricultural angle. You're talking about also prepackaged food system?
Yeah, like what in general, like from your perspective and experience, what is it that you think we still need to solve and resolve urgently?
Everything.
Yeah, but like first step.
That's a good question. It's the surfaces, like how do all of the systems come together? So how does the kitchen and the farm and the air filtration and the waste, like how does the surface system come together? What does it look like? Like how is it all going to work?
Okay.
Because right now everyone's working independently, like food scientists and space nutritionists, and then the agricultural science and plant scientists and fungi. It's like, how do we come together and talk so that we're learning from each system and designing something that holistically is working together?
Okay.
Because, and Omar, when you think about it too, like in that system, when you cultivate something and you harvest, what happens to it? You need to process it. And then where is that going to be stored? And then how long can it be stored for? And is it going to be refrigerated to minimize nutrient loss? Or is it, there's like that like end to end from farm to health and to the end product of eating and food production? What does that look like, and how is all that going to be integrated? Is probably, I'd say, the big picture, top-down approach that needs to be considered before because right now we're just bottom-up building stuff, but let's look at it from a top-down approach to see how could all these systems come together.
That's great. That's a great insight. Where do you see yourself working on 10 years from now?
Oh, that's exciting. Hopefully a mission where I actually get to go and run a pure food and nutrition mission in space. It would be my ideal goal. But where do I see myself? I think still trying to innovate the field of nutrition science, looking more at the bioactives, the impact potentially of aeronutrients, and bringing to Earth, some of that space nutrition research so we can make really cool discoveries that are going to help people eat better and thrive in their day-to-day through either food or air or their environment.
That's cool. Before we wrap up, is there anything else you'd like to share with our audience? What's new? What do they look for? Where can they find you? Something about Food IQ?
Yeah, sure. So if you want to stay up to date with everything that we're doing, you can follow us at Food IQ Global on all the socials. And as well, I'm Dr. Flav or Dr. depending if it's Instagram or Facebook or LinkedIn. So you can find me as Dr. Flav as well if anyone wants to reach out or would like me to come and give a keynote about how space makes the impossible possible.
It's been an honor to have you here. Thank you so much for sharing your insights and expertise.
Thanks for having me, Omar. It was lovely.
To everyone else listening, this is the Omar Al-Aili podcast. Thanks for joining us and keep exploring.